In this short video, I'll be sharing how I converted a battery-powered Christmas light set to run by USB power, so I can plug them into my phone charger or rechargeable battery pack, instead of constantly shelling out for AA batteries. And perhaps best of all, this cheap and simple conversion can be done without the need for any soldering. My particular lights are typical, a 2-meter string of 20 LEDs, with a battery box for 2 AA batteries, although the conversion equally works for longer strings with more batteries. And this is what I'm going to be using, a little micro USB socket bought from a major online retailer to replace the battery box. The obvious drawback of batteries is their lifespan, needing to be frequently replaced, so the costs soon mount up, even if you're buying supermarket brand ones. Now my lights have 2 functions. I can either have them flashing madly or on continuously. I could try and keep the flashing feature, but I'm happy to have them just on or off, which actually are labelled the wrong way round on my case. That'll keep everything most straightforward. The batteries and my USB supply are both DC, but the voltages are different. My 2 AA's add up to 3 volts, but my USB runs at 5, so it's not quite a case of replacing like with like, and we'll need to add a resistor. And just so I know how big that needs to be, I'm going to measure the current going through the system, so I can work out the wattage. You don't need to do this yourself, as I will let you know which resistor I used. But for anyone that's interested, I will be going through the maths a bit later on, which of course you can skip if you want to. But now, with batteries removed, let's get on with the wiring. And to work out what's going on, we need to get into this bit of the battery box, the cover for which pops out easily, revealing the switch and the battery connectors. And this is what we're here for, the 2 terminals of the LED string, nice and clearly marked as positive and negative. And we want to track our positive wire to the outside of the case where we can mark it, just using a red pen, before snipping off the 2 wires, as close to the edge of the case as possible, obviously with our red mark on this side. Then we need to separate the 2 wires just at the end, starting by splitting them with the scalpel tip, then peeling apart, just for a couple of centimeters or so, our positive wire still clearly labelled. We can now dispense with the battery box and turn our attention instead to the socket, which comes on a little breakout board. The input is the micro USB, which is still pretty universal, even with the arrival of USB-C. And then we have the outputs, the ground for negative, V-bus the positive. We can ignore the ones in between, as we're only using it for power, not data. Then we come to the resistor, and the one I ended up using was 56 ohms. The precise value isn't actually that critical, and anything between 50 and 100 ohms should do the trick. My choice was driven by what I had around, and a bit of testing, as much as the maths, which we'll come back to a little later on. But before that, let's get on with stripping the wire. I've already cut my positive a little shorter than the negative. This not only reminds us which is which, it also makes room for the resistor, which I'm going to put between the wire and the V-bus terminal on the socket, the negative wire going straight to the ground, where I'm going to poke the wire through the hole and then wrap it round. So I want a reasonably long bit at the end, twisted tightly so it doesn't fray. And here are our wires, all prepped and ready to go, the negative a couple of centimeters longer than the positive. But we're going to start with the resistor, poking one end through the hole in the V-bus terminal of the breakout board, leaving a couple of millimeters between that and the resistor itself, so we can bend back the wire and wrap it under itself as tightly as possible, so we've got a pretty good electrical connection. And just to make sure, we can crimp the ends with a pair of tweezers, flattening the wire against the terminal on both sides. Then we can do the same thing with our negative wire, feeding the end through the terminal and wrapping it back on itself. A little bit trickier than with the solid wire of the resistor, as even though tightly twisted, the end does fray a little, but that can all be tidied up with our tweezers before crimping to the terminal. Our shorter positive wire will attach to the other side of the resistor, twisting round about halfway down the leg, so positive and negative are roughly the same length. Then both wires will run side by side without any kinks, and with any final adjustments made, we can fold the remaining resistor wire back over itself so the positive doesn't slip off. And that's pretty much all there is to it, so let's give it a test, plugging in the USB cable and switching on my charger at the socket, lighting my string of LEDs with not a drop of solder in sight. And for comparison, I just so happen to have another set, so we can check the brightness of USB versus battery power, vindicating the choice of the 56 ohm resistor. And even though it's not soldered, our electrical connections are just fine, withstanding a certain amount of manhandling without any flickering. So it's out with endless AA battery replacements, and in with a convenient power supply to provide your Christmas twinkle. But of course, even though you don't need to solder, our connections will be that much more robust if you do. But soldered or not, there's one finishing touch I want to add, and that's a bit of heat shrink tube, slipped over the breakout board, and up and over the resistor and the wiring. This will not only provide electrical insulation, it'll also help stabilise our non-soldered version. And for shrinking, I'm going to use a hairdryer, set at maximum heat, which will magically shrink the tube around our components, making a tight fit over the socket, although there's a limit to how much shrink it's got, so we won't get it completely tight around the wires. You could of course just use insulating tape, but I think the heat shrink is that much smarter, and quite a bit more robust, making handling that much easier. And that's our conversion complete. All the convenience of USB, either powered by charger or battery pack, a step up from AA's. Last of all, I want to go back to the maths, as I promised, for anyone who's interested in how I came up with my sums. And for this, I've got some basic equations, familiar to any GCSE physicist. The power of my electrical system is equal to the current, I, times the voltage. And back at the start, I measured my current to be 48 milliamps, or 0.048 amps, and the combined voltage of my two AA's is 3 volts, making the power 0.144 watts. And I want this to be the same when I step up to 5 volts. With another equation, I can also work out the resistance, which is the voltage squared over the power, which I know from the other calculation. So the sum is 9 divided by 0.144, which works out as 62.5, and that's in ohms, the unit of resistance. And no, I didn't work that out in my head, I had it written down from earlier. Now we need to know what resistance is required to deliver the same wattage at 5 volts from the USB power supply, so our LED string is getting the same amount of juice, and our individual bulbs won't be overloaded. So using the same formula as before, we can calculate the desired resistance as 5 squared divided by the same power as before, 0.144. which comes out as the considerably larger 173.6, which is where our additional resistor comes in, added in series to the LED string, which had a resistance of 62.5, which I'm making rather large assumption hasn't changed at 5 volts, so we can subtract that from our total, giving the value of the additional resistance required, as around about 110 ohms. But when I came to do mine, I couldn't find one of those in my resistor box, the closest being 56. Giving me a combined resistance with my presumed 62.5 of 118.5. And to work out the impact of that on the power, we can rearrange the resistance formula, which comes out with a new total of 0.21 watts, which whilst it's slightly larger is very much in the ballpark of what we had before, so very much in the operational parameters of our LED string, and not likely to blow anything, with the added bonus of making everything a little bit brighter. A definite win-win over the battery version,